In this video, we're going to talk about the preparation of carboxylic acids, including natural sources as well as some synthetic methods. So there are a lot of carboxylic acids that are produced in nature. Some of the simple ones that we've already mentioned, formic acid. This is made by some ants, and this is acetic acid, which is the major component of vinegar. We have amino acids that make up our proteins. This is lactic acid, which builds up in our muscles after a really hard workout. This one is salicylic acid, which could be extracted out of willow bark and used as a pain reliever, but it was a little bit harsh on the stomach, so then the acetyl ester of it was produced. This is acetyl salicylic acid. It has the same pain relieving properties, but it does not affect the stomach in the same way. This is better known as aspirin. And then finally, here we have some examples of fatty acids. The naturally occurring fatty acids are all even numbered because of the biosynthesis, which takes part 2 carbons at a time. But these come both as saturated and unsaturated. And when these fatty acids are combined with glycerol to make triacylglycerides, then the form of the triacylglyceride depends on the composition of the saturated or unsaturated. So, for example, if all of the fatty acids are saturated, then your triacylglyceride is a fat, whereas if you have some unsaturated fatty acids, then your triacylglyceride is an oil. We will talk about these a little bit more at the end of the semester, but for now we're going to take a look at some synthetic methods to prepare carboxylic acids. Most of the methods for preparation of carboxylic acids we've already seen. So if we have benzene with an alkyl side chain, if there's at least one benzylic hydrogen, then this can be oxidized with sodium dichromate, potassium dichromate, and this gives us a benzoic acid. Keep in mind there has to be at least one benzylic hydrogen. And keep in mind that even if this is a long chain alkyl group, when it's treated with these conditions, we're not going to isolate the long chain carboxylic acid, we still isolate a benzoic acid. Also keep in mind that the alkyl oxidation is limited to being aromatic side chains. So regular alkyl groups are not going to be oxidized unless we're talking about the benzylic position. Using the same conditions, though, we can oxidize either alcohols or aldehydes up to carboxylic acids. So chromic acid can be used to oxidize a primary alcohol to a carboxylic acid, and it can be used to oxidize an aldehyde to an acid as well. Another method to prepare carboxylic acids that we've already seen is the carboxylation of Grignard reagents. So if we have a Grignard reagent, and this is reacted with carbon dioxide, the Grignard can add to the carbonyl carbon, push these electrons onto the oxygen. It doesn't matter whether we imagine this way or this way. And that gives us this intermediate, and then with aqueous acid workup we will get a carboxylic acid with one additional carbon beyond what we started with in the Grignard reagent. Here's another example, and now we're starting with the bromide. So this has to be treated with magnesium metal, to give the magnesium bromide, and then it can be reacted with carbon dioxide to give the carboxylate, and then finally step 3 aqueous acid workup will give us benzoic acid. Keep in mind, if you are trying to make a particular carboxylic acid, you would want to think about this piece as your Grignard reagent, and then this piece would come from carbon dioxide. But it's also important to keep in mind the reactivity of Grignard reagents. You have to make sure that there's nothing else in your target that is acidic or that would otherwise interfere with the Grignard reagent. Another common approach to prepare carboxylic acids is the hydrolysis of nitriles. We've seen a few examples of how to prepare nitriles. So for example, if we have an alkyl halide and we treat it with sodium cyanide, we can do an SN2 reaction to give, in this case, this product. We also saw more recently that if we have an aldehyde, we can treat it with CN- followed by aqueous acid. Keep in mind, here we're talking about nucleophilic addition to an aldehyde, and so we get this, and then with dilute mild aqueous acid workup, we get a cyanohydrin. So we know a couple of ways to make nitriles, but now once we have a nitrile, if this is treated with HCl and water, or it could be hot aqueous acid, then this nitrile is converted to a carboxylic acid. So in the first case, we would make this, and in the second case, we would get this. We still have our OH, and now we have a carboxylic acid. So this gives us an alpha hydroxy carboxylic acid. We're going to talk about the mechanism later when we talk about nitriles, so later in this chapter. For now, I want you to recognize it as predict the products, okay? This can be a little bit ambiguous because with sodium cyanide, we have this intermediate, and then we treat it with dilute acid to protonate the O-, but it's harsher conditions then. So more concentrated acid, adding heat, so more forcing conditions will convert the nitrile to the carboxylic acid. So finally, let's look at a few examples and select the reagents to convert a starting material to a carboxylic acid. Actually, what we're looking at is the same starting material, but being converted to 3 different products. So in the first case, we have ethanol, a primary alcohol, being converted to acetic acid. So we still have 2 carbons, so we're not adding any carbons. This one is a simple oxidation. So we can use sodium or potassium dichromate, sulfuric acid, and water. And this is going to oxidize our primary alcohol to a carboxylic acid with no additional carbons. In our next example, we are going from a primary alcohol to a carboxylic acid, but we started with 2 carbons and our target has 3 carbons, so we need to add an extra carbon. So we can treat our alcohol with HBr or PBr3 to give an alkyl halide. Now from here, we have a couple of options. One option is that we can treat this with magnesium to form the Grignard, followed by carbon dioxide, followed by aqueous acid workup, and that would give us this carboxylic acid, which is our target. Alternatively, from Alternatively, from the bromide, we can treat this with cyanide to give the nitrile, and then this can be treated with HCl and water to hydrolyze the nitrile to give this carboxylic acid. So in this case, we have two different ways that we can make our target. So notice, we're trying to convert an alcohol to a carboxylic acid with one additional carbon. In this case, it works to do the Grignard route or to do nitrile substitution followed by hydrolysis. We are going to come across some examples where maybe only the Grignard way will work and not the nitrile, and other examples where only the nitrile approach will work and not the Grignard. So be on the lookout for that. Finally, in our last example, we are going from a primary alcohol to a carboxylic acid with one extra carbon, and it is an alpha hydroxy carboxylic acid. So, in this case, it might be a little bit easier to think backwards because we know that this, along with the acid, this could be formed from this cyanohydrin. Well, this cyanohydrin can come from this aldehyde. And then this aldehyde can be made from this primary alcohol. So going in the forward direction from our alcohol to an aldehyde, not to a carboxylic acid, we want to use PCC or PDC or the Des-Martin pyridinane. From the aldehyde to the cyanohydrin, we want to use step 1, we add cyanide, step 2, dilute acid, and then to hydrolyze our nitrile to the carboxylic acid, here we need more forcing conditions, so more concentrated HCl and water and possibly heat. So from the same starting material with different sets of conditions, we can make a number of different products. So it's important to keep in mind the different features of these reactions, and like always, remember to count your carbons.